So recall that if we have a simple closed curve, then this has two orientations. We can traverse it counterclockwise, or we can traverse it clockwise. And when we defined the integral of a vector field over our curve, this changed sign, if we did it like this, then this integral changes sign when we reverse the orientation. So we're going to do something similar for surfaces. For surfaces, and you might expect, like, it's not immediately obvious that in going from, so like in one dimension, there's exactly two orientations. And you might not necessarily expect that to hold in higher dimensions, but it is still true. So for surfaces, orientations will, in some sense, distinguish inside or outside. Well, maybe this is only a good definition for something like a sphere. Maybe a better way to say is, in general, it's just distinguishing two sides. So if we just take a sheet of paper, an orientation is going to say, okay, is the top side sort of the privileged side, or is the bottom side privileged one? If you're dealing with this case of a sphere, then if you were holding a spherical object, then you probably care sort of about the outside of the sphere. But if you're dealing with some problem that's in a spherical chamber, then you're more interested in the inside of the sphere. So an orientation is going to give us a way to distinguish two sides. Because remember, a mathematical surface, as it's defined, is like infinitely thin. It doesn't even really have a concept of two sides. So that's what the concept of orientation is providing. Okay, so formally, an orientation of a surface S, I should say smooth, all our surfaces are smooth, is a continuous choice of unit normal vector that we'll write n. So for instance, for the sphere, we could actually take this normal vector to be the same vector as the vector pointing from the origin to the sphere. So it's n, x, y, z, and it's defined for, this is defined for x, y, z in your surface, and it has to always be normal to the surface. So here I said a unit normal vector, but we could also, it's equivalent to ask for a non-vanishing normal vector. Because if we had a normal vector, let's say big N, x, y, z, and this is always normal to the surface S, and it's not necessarily a unit vector, but it never vanishes, then we can get a unit normal vector, little n, by taking this and then just making it a unit vector by dividing by the magnitude, which, and in order to do that, we need this to never be zero. So a surface is orientable if it admits an orientation. And an oriented surface consists of a surface together with a choice of orientation. So notice that, pay attention to the difference between orientable and oriented. So a surface is either orientable or not, and that's just a property of the surface. An oriented surface is really a surface plus some additional data of a choice of orientation. So if we've got a connected surface, actually a connected orientable surface, admits exactly two orientations. So if if n is one of them, the other is negative n. So the fact that in one dimension you only have two directions, this carries over into higher dimensions. We still only have two orientations, because even if our tangent plane here, our tangent plane is two-dimensional, the normal thing here will just be one-dimensional. So this is for a connected orientable surface. In general, a surface, I should say an orientable surface, with k components. So if your surface consisted of a sphere and of two spheres, or maybe in a plane, has 2 to the k orientations, because on each component we have two choices of orientation, and those are all independent. So if our surface consisted of all two spheres and a plane, we would have 8 possible orientations. Okay, so as I've shown here, a sphere is orientable. So any surface which is the boundary of a region in space is orientable, because then we can take the normal vector to point away from the region. So a sphere is it's a two-dimensional object, but it's the boundary of a solid ball, which is a three-dimensional object. Or similarly, a torus, as we've defined it, is sort of just like a shell, but you could also fill in the torus. So a torus is also orientable. If we took just a flat sheet, this is not the boundary of a region in space, but this is still orientable. But there are surfaces which are not orientable. So the standard example of a surface which is not orientable, is the Mobius strip. So the theory of integrating vector fields over surfaces that we'll develop is going to require a notion of orientation. You can do this for things like the Mobius strip, but it's more complicated and we won't sort of need to deal with that. So this is a graphic of a Mobius strip, you can make a Mobius strip physically yourself by taking a thin sheet of paper. And now if you attached the edges together like this, so what I mean by these two arrows is like this part you would glue to this part you would attach to this part, then that would give you a cylinder. To get a Mobius strip, what you want to do is instead, so I'll write it like this, and this means like this edge gets attached to this edge, this point gets attached to this point, and similarly like this would go to here. So what you do is you take this sheet of paper, you twist one of the edges, and then you attach it together. So let me explain how to build a parametrization of the Mobius strip. So like how I drew this figure. So if we started out with a parameterization of a cylinder, let's say we took x equals cos theta. Actually, it'll be better to do it this way. So let's take r of theta and t is cos theta I plus sine theta j plus tz and we'll take theta between 0 and 2 pi as usual, and then t between 1 and -1. So you think about this is this part is just giving you a circle. Now the z part, we're sort of going around the circle and drawing a straight line at every point. So this gives you a cylinder. To modify this to get a Mobius strip, we want to instead, so if this is our circle, we want this line to instead, let me point it. We want this line to sort of twist as we're moving around. So that by the time we get back, it's still vertical, but now pointing downwards. So how we do that is, and so I want it to tilt like inwards towards the origin, or maybe outwards. It doesn't matter, like inwards or outwards, just that it's moving in the line like parallel to the xy. So we'll start out with cos theta I sine theta j as before, but now we'll add t times, instead of just an up and down k like this, something that's tilting. So I want, right, if the tilting is sort of like this, then I would put, if I want it to start upwards, then I'll put cos theta and sine theta here. But actually sine theta, so the theta is like where I'm moving around. If I want it to do exactly one twist as I go all the way around, then I should divide this by 2. So we'll have sine theta over 2 times this thing, cos theta I plus sine theta j, and then cos theta over 2. Okay. If you wanted a band that did many twists, you could add like an n variable here, and that would make it twist n times. So you don't, again, this is not going to be on any sort of the homeworks or anything. This is just something kind of neat. So from here, I guess if you were brave, you could try to work out like r theta cross rt, and could see that this vanishes on the interior of the parameter domain. So a warning
in the shape of a Mobius strip, inverted, please.
So in Avengers Endgame, which has many plot holes, but this is one of them. Tony Stark uses a Mobius strip to invent time travel. And yeah, so this will not actually work in reality.